we're mostly not interested in processes that occur at constant temperature because there aren't very many of them. So melting and freezing are special cases. But we've been interested for a while in things related to transfer of energy due to a temperature difference, changes in thermal energy of objects that are in thermal contact with something that's at a different temperature. So we put blocks of different sized blocks of aluminum at different temperatures together, and we calculated the energy changes, and we used the specific heat capacity to do that. And so we're interested in seeing if we can understand how specific heat capacity of a material is related to this microscopic explanation of energy flow that we've been looking at. So one of the things to think about is what specific heat capacities are. So here's some substances, here's some metals, because we're talking about metals mostly. So here's aluminum, and the specific heat of aluminum in joules per Kelvin per gram. Remember, it has to be on a per something basis, and typically it's just given in the literature. Gram is 0.897. And iron is 0.450. And copper is 0.385. And gold 0.129. And there's some others, but that'll do. So they're different. But we've been calculating by gram. I wonder what we'd see if we calculated on a per atom basis. So let's convert this. Instead of joules per Kelvin per gram, we want heat capacity in joules per Kelvin per atom. So what we need to do is figure out how many atoms are in a gram, right? So we need the atomic weight. In grams for aluminum, it's 27. Okay, so let's just convert it to specific heat on a per atom basis. So how are we going to do this? Avogadro's number is certainly going to come in there. So we've got 0.897 joules per Kelvin gram. That's the specific heat capacity. And then we've got 27 grams per mole. And we've got 1 mole, or 6.02 times 10 to the 23rd atoms. And so, let's see, the unit's going to work out right. We've got grams cancel and moles cancel, and we come out joules per Kelvin atom, which is what we want. And if we work that out, it comes out to 4.02 times 10 to the negative 23rd joules per Kelvin. So we'll put this over here. Okay, so I want you to do the others. So if you're sitting over here, I want you to calculate for iron, and if you're between here and here, I want you to calculate it for copper, and you guys over here need to calculate for gold on a. That would probably help. So iron is 56 grams per mole, and copper is 64, and gold is 197. Yeah, why don't you just tell me what the answer, what you're getting? Joules per Kelvin. Anybody else get a number here? 4.22 times 10 to the negative 23rd joules per Kelvin for gold. Iron. Per atom. Now, the interesting thing about these numbers is that they all look roughly the same. These very different metals, when we actually work it out on a per atom basis, it's sort of 4 point something times 10 to the negative 23rd joules per Kelvin. And in fact, it turns out that classically, thinking not using quantum oscillators, but just thinking about how these things move, there's actually a prediction that the specific heat capacity in joules per Kelvin atom should be 3 times the Boltzmann constant per atom. And that really is pretty much what it comes out to, because 3 times the Boltzmann constant is about 4.14 times 10 to the minus 23rd joules per Kelvin. So this is pretty good. This looks pretty much like 3 times the Boltzmann constant per atom. And that really has to do with the idea that you can put energy into 3 different directions. It can be back and forth, and it can be up and down, and it can be, so X, Y, and Z. So sort of 1 times the Boltzmann constant per degree, what's called the degree of freedom, way it can move. Really, it's half K for every energy term. So there's the half K for the kinetic energy in the X direction, half A for the spring, K for the spring energy in the X direction. So about, anyway. So it's pretty close. People were really pretty happy with this prediction until about 1911, when a Dutch physicist named Kamerlingh Onnes made the first really, really good refrigerator where you could get things down very, very cold, close to 0 Kelvin. And then people were just amazed to discover that the specific heat capacity on a per atom basis wasn't this at all. It was really different. It changed. So it depends on temperature. And in fact, these are measurements that were made basically at room temperature, which is all people could do until the beginning of the 20th century. But once they started measuring at other temperatures, they found that it didn't look like that at all. And we can see that actually from looking at, we can actually calculate the temperature of one of our aluminum nanoparticles or lead or whatever we're doing as a function of the energy we put into it. And so we can actually, because I remind you that we can calculate, if we can calculate a delta S, and we know a delta E, we get the temperature. So if we just keep putting energy into one of our blocks of aluminum, keeps getting warmer and warmer, we keep calculating the amount of energy we put in, the change in entropy, the temperature. We should be able to get a plot of temperature versus the amount of energy we put in. And when we do this, it looks like this. So remember that we looked at some plots of number of ways of arranging energy versus energy. So we basically were plotting entropy as a function of energy for two blocks in thermal contact. And remember, it looked like this. So we have a two block. This happens to be a, well, this is some generic block because we don't know the energy of one quantum. So we're plotting the log of the number of, so log of omega, log of the ways of arranging energy versus the number of quanta of energy put into block 1 when we have two blocks in contact. So that was the entropy of block 1. The red line, the blue line was the entropy of block 2, and the magenta line was the entropy of the total system. And when the entropy was a maximum, that was equilibrium. Well, we can just take the next step and calculate temperature as a function of the amount of energy we put in. So here's the same thing for these two blocks. And what we're plotting here now is the temperature of the block as a function of the amount of the total energy that's in block 1. So amount of energy in block 1 goes up, temperature of block 1 goes up, that's the red line. Amount of energy in block 1 goes up, temperature of block 2 goes down, that's the blue line. What's the slope of this line? No, I mean, what is the meaning of this slope? The slopes are equal and opposite where? If this is temperature, if this is a plot of temperature versus energy, does the point where these lines cross mean something? Really? What does it mean? Yeah, there we go. So when the temperatures are equal, the entropy is greatest, and that's what we expect at equilibrium, right? Yeah. Okay, so here it does matter. What's the slope of the line? This is a plot of temperature versus energy. Do we have any equations that relate temperature and energy? So what is remember this one? So the specific heat, the change in thermal energy was the mass if it's on a per gram basis times the specific heat capacity, delta T. So change in temperature with respect to energy is related to, okay, so we have delta T over delta E. That's what that graph, the slope of that graph is, right? Change in temperature as you change the energy. Yeah, that's right. It's going to be 1 over C modulo some m's here. If we do it on a per atom basis, then that just comes out to be atoms. So actually the slope of this, either of these curves, the slope of the red one's easiest to think about because it's increasing. The slope is the heat capacity of this object. But notice that, is the slope constant? It's pretty constant here, but is it constant here? No. That means the specific heat capacity is actually changing with temperature when the block's at a low temperature. And that was what surprised everybody. So we actually ought to be able to crank through a calculation and predict the specific heat capacity on a per atom basis for one of our little microparticles of something by actually just taking the slope of this line. So that's what we're going to do. I'm going to do it by hand first. Then we'll let a computer do it for us. So we're going to do aluminum. And here's some things we need. We need the value of the Boltzmann constant. We've got that. A couple days ago in a clicker question, you calculated the amount of energy in one quantum for aluminum. So you did this calculation using the mass of an aluminum atom. Okay, and so for aluminum, 1 quantum of energy came out to be 3.96 times 10 to the negative 21 joules. So we're going to need that. So what we're going to do is we're going to take a particle that has 50 aluminum atoms in it, and we're going to calculate its specific heat capacity when it's kind of cold, when it doesn't have that much energy in it. And so we're going to start, so we're going to have 50 atoms of aluminum, and we want heat capacity at when it's cold, low temperature. So let's start with, we're going to put 10 quanta of energy, 10 of these quanta into our little 50 atom system. And so we're going to have to get, so specific heat capacity seems to be, or 1 over C was, so we have delta E thermal is C delta T. So and C has units. What are the units of C? Joules per Kelvin, right? So we better have delta T. Okay, so what's omega for this? What are the number of ways of arranging 10 quanta of energy among 50 aluminum atoms? 50 atoms, how many oscillators? 150. Okay, what's the number you got? 2.13 times 10 to the 15 ways of arranging energy. So what's the entropy then? Really? Okay, 4.870 times 10 to the negative 22. This is units of joules per Kelvin, which we got from the constant. Okay, now we got to get a temperature. So we need, temperature is delta E over delta S, so we need a delta S. So what's delta S? Uh-oh. We don't have a delta S. We've only got one S. You can't have a delta S with one value of entropy. So it looks like we need another value. So we better do it with 11 quanta. So what's omega when we've got 11 quanta? I'm going to keep a few more significant, well, okay, that's fine. We'll do it that way. 3.101 times 10 to the 17. What's the entropy? 16. 5.240 times 10 to the what? Negative 22. Okay, now we can get a change in entropy, right? Because we have two entropies. So what's delta S as we added times 10 to the minus 22? 23. Okay, so what's the temperature? So what was the change in energy going from 10 quanta to 11 quanta? 1 quantum. And what's the energy of 1 quantum? Okay. So we have that. So the temperature is, okay, we have 107 and we have 0.009. We need another number. Someone else better pull out a calculator. So it's 107.2 Kelvin. Okay, that's awesome. So that was, you calculated delta E over delta S to get that. So now we need the specific heat capacity. And so what we need is a delta E over delta T, right? Uh-oh. We only got one temperature. We better do it again. Okay, so 12 quanta. So how many ways are there arranging 12 quanta among 150 oscillators? 4.160 times 10 to the 17th. Is that, what's the entropy? Okay, what's the change in entropy? 3.5 what? 86 times joules per Kelvin. And that corresponds to a temperature of 110 point what? Is that what you got? 110, 4, 5, 4. Okay. And now it looks like we can get a specific heat capacity because we have two temperatures. So what's delta E over delta T here? There's no such thing as delta E per atom. Oh, it just means that it's just the atomic. It's this quantity is what it's trying to tell you. It's this one quantum of energy, but there's no delta E per atom. What's this number? What is the heat capacity of this object? Say again. Okay, 1.2375 times 10 to the negative 21. And what are the units? Joules per Kelvin. But what does that come out to? So that's for this entire particle, though. That's for 50 atoms, 100 oscillators. That's not on a per anything basis. It's just for this object. So we want to get it on a per atom basis. Well, there's no such thing as delta E per atom. There's specific heat capacity per atom. So what does that come out to? So what is it per atom? How many atoms did we have? 50. 2.45 times 10 to the negative what? Okay, so with a fair amount of work, we find that at a fairly low temperature, somewhere between 107 and 110 Kelvin, the specific heat capacity for aluminum, and this was 50 atoms, and delta E was 3.96 times 10 to the minus 21 joules. Is that what it was? Yeah. So we find with a fair amount of calculation that we predict a specific heat capacity that's actually about half what it is at room temperature. So that means probably it's going up as temperature goes up, right? So, and so, by the way, problems of this kind tend to appear on tests, so it would be a good idea. Okay, so what is this? Let's get so we can see it. What the dots are is actually data from the research literature, from reference literature. This is measured specific heat capacity for two substances. The red dots are specific heat capacity of aluminum versus temperature, and the blue dots are measurements of the specific heat capacity of lead versus temperature. Okay, aluminum's sort of stiff and light, and lead is sort of squishy and massive, and so it's not terribly surprising that they'd have different specific heat capacities. And it's on a per atom basis. Or it's been, I mean, you don't see it that way in the literature, but we did the conversion we did here. And so these are actual data. And so what we're going to do is ask this program to do the calculation we just did. Take an aluminum nanoparticle, a few hundred atoms, and start shoving quanta of energy in one at a time, and calculate the number of ways of arranging the energy and get the entropy, and then from two adjacent ones we get a difference in entropy, we can get a temperature, and then we need two temperatures to get a delta E over delta T, which gives us a specific heat capacity at that temperature, and then we just kind of crank through doing it. Aluminum, using the spring stiffness for aluminum and the mass of an aluminum atom, our predicted curve actually predicts that not only that the specific heat capacity will rise with temperature, but it actually goes through the data. Now, why doesn't it really quite, so where does it level off? It levels off at 3K per atom. And why is it not quite, why are the data really not level? Because when something gets really hot, then the fact that we don't really have this ideal harmonic oscillator anymore, we're sort of starting to get out of the parabolic part of that potential energy well and into the slightly slopey one, and so it's not quite. And then we change the calculation, same calculation, except we use delta E for lead based on that spring stiffness and the mass of a lead atom. And we see that it goes through those data pretty well. So this is a really simple-minded model. Balls and springs. That's what a solid metal is. Little balls connected to springs. The balls have the mass of the atom, and the springs have the characteristics of the chemical bond. We measure the interatomic spring stiffness by hanging weights on a wire and just seeing how much it stretches. And yet we can actually use that model to predict, by knowing that these little masses and springs are quantum oscillators that you just put energy in little packages. We can actually predict the specific heat capacity as a function of temperature at low temperatures, something that people didn't even know was different until 100 years ago. And so this would have been a Nobel Prize in 1911. And we can do it for two different substances, and we actually get a pretty good fit to the data. So that's moderately impressive for a simple model. Take it seriously, crank it through. I don't think we probably suspected when we started stretching wires that we'd be able to get a prediction like this. So this is a fairly impressive triumph of a simple model and some fundamental principles and some fundamental ideas. In lab who's had lab this week? Some of you have. Okay, so you've actually done the calculations to calculate entropy as a function of adding quanta and temperature and whatnot. You unfortunately don't have time to do this one. You could, but that actually sort of puts teeth in this model and makes it a pretty interesting endeavor.